Great. My name is Ismael Martinez. I am presenting today's competition. It's hosted by Google AI and it's Quickdraw Doodle Recognition Challenge. Quick thing about me. So my name is, again, Ismael Martinez, although most call me Izzy. I have a bachelor's in math and computer science from SFU, and I will be starting a master's in a little under a month, actually, at University of Montreal in computer science and operation research. A little side note, this is my techie side, but I have a blog in cryptography and operation research and these type of things that you can look at. All right, so on to the actual competition. So Quickdraw, if you were to search up Quickdraw at the link down below, then you'll find a little game per se where Google gives you a label and you have to try to draw that label. You can do it on your phone or you can do it on your computer. So these are some examples if it gives you the word bee and you have to draw a bee. And then Google AI will attempt to classify that image. And if you actually play, it will talk to you while you're drawing it. So it'll say, I see circle, I see fly, I see, oh, I get it, I see a bee. So what we are given is in the competition is 50 million drawings and 340 categories. These are, oh, there's a question. Two.
Might be the same one.
Maybe.
Yeah.
This seems like a fun game.
Give it a go.
Do you think that there is a risk of somebody, drawing a important feature of a bee and the algorithm saying that's a bee and then the people stop drawing the entire image of the
Yeah,
bee?
so, if we actually look at this, you can see my squirrel is unfinished and my hand is unfinished as well, right? It's a limbless squirrel. It's a limbless squirrel, right? Because I would imagine the important feature being a curly tail, right? With the hand, the important feature I imagine is a thumb with one or two fingers because I never actually finished it. So in the competition, you are given incomplete drawings and also drawings that don't necessarily match a label. So if you look at here, it may be a little small to see, but underneath you can see little X's and check marks. That's whether Google AI was accurately able to classify that image. So for my toilet, it couldn't get it, for example.
So my question was, how diverse are the categories that they have the images from?
So we will look at some examples of the categories in a bit, but you'll see things like plane and you'll see things like horse.
Okay.
Right.
So you gave the example earlier that it might say this is a fly or this is a bee. Are there lots of insects, for instance, in the class? Are there lots of similar things?
So we will look at instance of unrecognized images or the highest chance of being unrecognized, and you'll see a pattern of there's horse, there's cow, there's pig,
okay.
there's all of these quadrupedal animals in there. Somebody's playing it. I can hear it. So the objective train a model to classify doodles into one of 340 categories. Actually, we'll see it's essentially 3 of 340. We'll see that a bit in a second. Submission, so the key ID of the image, followed by your 3 image classes in order, right? So in these cases, the Eiffel Tower is your first pick, airplane your second pick, donut your third pick.
That's really weird.
Yeah, I don't know what this drawing could be, but
Draw that.
yeah, so evaluation metric. So it is mean average precision at 3. So U being the total number of scored drawings. So in our test set, we have quite a bit. We have 112,200, and the P of K is the precision cutoff. So we'll look at that a little bit more in depth in the next slide. And N is the number of predictions drawings. So I don't see a reason why you wouldn't put 3 all the time, because it doesn't affect you negatively if you put up to 3. So always put 3 there. So mean is going to take it the average of all of yours. So let's look at a single example here. So the average precision at 3. So In this case, I remember I said that you can pick up to 3 and in order. If you were to pick the correct thing on your first try, your cutoff is 1 and you get it correct on the first try. So your average precision at 3 is 1. In the second example there, you get Eiffel Tower second. So your cutoff is 2, you get a second, so you essentially get 0.5 because you get 1 out of 2. On the third one, you get it third, so you get 1 out of 3. And on the fourth example there, you don't get it at all, so you'll get 0. So I tried my best to draw something that would resemble all 3 in a way. And then the mean average percent of 3 just takes the average scores of all of your 112,000 examples. So leaderboard, that's me at the bottom, unfortunately. There was about 1,400 people in this competition, and Alexi, you can see number 8 there. Well done, Alexi. So top score was 0.9548.
46 submissions too.
Yeah.
The least of the top 10.
Yeah.
But you can see how close they are, right? Mine was 880th, and I got 0.86. So there isn't a whole lot of room for error in that space. What data are we given? So country codes. And there, we'll see later, there are, I think, 84 different country codes, 2 character strings. The drawing, which is a set of vectors that describe the drawing. Your key ID, unique identifier, your timestamp, and the word, the actual label. And as well as there's a recognized flag, a Boolean flag, which is whether Google AI was able to classify this correctly or not. So it's going to be 1 if yes, 0 if not. And a little asterisk there. So the first 3, country code, drawing, and key ID, these are what's given to you in the test set. Meaning the test set does not have the recognition flag, timestamp, and of course, not the label. How much data? 73 gigabytes. Like I said, 50 million drawings are given to you. And we will see as well, we are given 2 files per class. Yep.
I was just wondering, this seems like a very strange train test split. Do you have any idea why they went for that ratio?
What do you mean?
Well,
like the number?
Yeah, they've only got like 2% of the total records in the test set.
That I don't know. Maybe Alexi can.
I'm under the impression that they like manually verified the labels in the test set. So there was like a substantial cost to labeling that. And so that's what kept it small.
Whereas with the training set, that's just what's ever output with the game. So it's the recognition flag used on my drawings, it has the X and the check, so everything is automated. Going into the data, like I said, 2 CSVs per class. So we had a raw file and we had a simplified file. And there's something that I didn't put here, but we do go into it a little bit. So the simplified takes out unnecessary points, but it also has time metrics in the raw file. So we will look at that. As a result, the raw is much larger than the simplified. So if you're like me and have a very small GPU, and then you're going to be using the simplified so that it doesn't take you a week to train. But with people who have the resources and have the time, then absolutely the raw file will give you better results. Going into the drawings, so this is just looking at the simplified first. This is one record, and these are the vectors that represent an image. It looks a little daunting at first, but let's try to break it down a little bit. So here I've color-coded it to look at X and Y splits. So the first pair, blue and red, that's your first stroke. Second pair of blue and red is your second stroke, and then third one is your third stroke. Now, this is a generalized form of it, and our strokes are between 0 and 255. Or our point values are between 0 and 255. Looking at the raw, we have this third metric in the green, and that is your time. So in milliseconds, so we see there on the first one, 0, 20, 45, and that's basically the timestamp in milliseconds of when these points were recorded for the appropriate X and Y. And for these ones, so the first one was 255. These ones, it looked like X and Y were between 0 and 18,000. And the time steps, because we had to do everything under 20 seconds, then they would be under 20,000. Country codes, there were, again, 84 possible country codes. So the top ones, US, Great Britain, Australia, India, Canada. Those ones are ones that we expect. Bottom 5, I wasn't 100% sure on what these were, but my guess, Bahamas, Armenia, Puerto Rico, Lebanon, Tunisia, could be Thailand. And just a quick aside, because I'm going to show some pictures of images in a second. This is the default Matplotlib color scheme. So your first plot's going to be in blue, second in orange, third in green, and fourth in red, because we are going to look at these. So I just picked some random images and plotted them and took a look at what strokes, in what order do people draw things, right? So we look at the anvil, and the rectangle was drawn first, followed by orange, so the base of the anvil, and then the head next, right? And then we look at the baseball, so circle first, and then the left, right, and then the stitching. Some of them are a little odd, so the bats at the bottom, ears first, it's kind of odd. I wouldn't start that way. Bulldozer with the colors, you may not get this without the colors, or see this as well, but the bulldozer on the far left, drawn in one go, right? And then we can also start to see what features might be important, because we look at the bottom, the boomerang versus the banana on the left and the right bottom. We see really the only difference would be the stem is colored in for the banana. Otherwise, they look about the same. And these are all with the recognized flag being true. So these are purely ones that Google AI did classify correctly. And to make it a little easier on your eyes, at least it was easier on my eyes, remove the dots, get a better sense of what these drawings actually look like. A little bit of statistics about the data. So these are records per class, so we can look at how many records there are. Little table on the side. So the most popular records are classes. Snowman. There are 340,000 snowman drawings. I don't know why. And potato. That one makes sense to me. My guess, I played this game a couple times, and you can just exit out. So perhaps if you exit out, it doesn't count. Maybe that's one reason. The harder ones people are not doing. It could just be that that Google is throwing the ones that are most popular per se. But yeah, so snowman, potato, calendar, these ones seem pretty simple. And then panda, bed, ceiling fan at the bottom. Ceiling fan is particularly difficult, I find, for some people to draw. Now let's look at just the recognition. So when recognize is equal to true, this is when Google AI says, yes, we know what that is. We see very similar spread near the top. And at the bottom as well, panda was at the bottom before. Stove is now in that group. Unrecognized. So this is when Google AI does not know what this is. And the most unrecognized ones are teddy bear, horse, and this is what I was talking about before. When you see all these quadrupedal animals, horse, cow, elephant, pig, yeah, you'll see those a lot. Also with the car, I know that there's car, there's truck, there's bus in there. So it does make sense that some of these would get confused with others. And then finally, I want to look at proportions. So this is what proportion of recognized versus unrecognized there were. Did you have a question?
Yeah, I just thought that spike on the last graph was interesting.
Yeah.
Is that, yeah, that doesn't seem random, right? Like maybe they just stopped giving people these records once they hit almost 22,000. Do you have any interpretations of this spike?
So my interpretation is that there are certain classes that are just extremely difficult. Like it seems like there's a bulk of moderately easy, and then there's a chunk of just very hard ones, or that Google AI just couldn't get. That's my only guess as to what that would be. Alexi might have something.
I mean, this is like classically what a distribution looks like when you like chop it off and take a long tail and sum it, right? So they've probably, I bet you a lot of those classes have a way higher proportion unrecognized than even this. And then when they were picking data, they threw a lot of unrecognized data out. Yeah.
Yeah, that's the other thing as well, because they had something like 1 billion images total, right? So they could be pretty selective in terms of how many recognized / unrecognized ones they put in.
Yep, there are 1 billion total. We are given 50 million. So, and then, like I was saying, there's the proportions of recognized versus unrecognized. And yeah, that's a table on the end there. So now I want to do a little quick summary or review of convolution neural networks, because the first place uses everything. So I'll look quickly at ResNet, ResNext, DenseNet, and CeresNet, CNET, those ones. Hopefully we know what a convolution is, otherwise there's going to be way over our heads. But starting with ResNet, so we have this. This is a single residual block that has an identity path that kind of skips. It's kind of like a shortcut, skips paths and just goes straight down. And that's one residual block. With ResNext, or with, ResNext, instead of this single path here, instead of this single path that goes down, now we actually split. And we can go down many paths. We add an extra parameter of cardinality. So this one has cardinality of 32. But it is based on ResNet, so we still have our identity path that comes down. Next, we have DenseNet. So where we had, with the ResNet, where it skips over, DenseNet is going to go and do a skip for every single one of these. So it's going to be fully connected all the way down. And that is one single DenseNet block. And so we see at the bottom that we have multiple of these dense blocks, and that form the full convolution neural network. And then this is something that I found interesting. I don't know if some people here have experience with this, but it's called squeeze and excitation. So those are your CNETs and CeresNets and so on. So what we do is first we do a squeeze. And in this squeeze portion, we'll take a global average pooling of your feature maps of each channel. And so we have one value per channel. And then you do an excitation where you take those. So if you have, say, 64 channels, then you're going to have 64 of these squeezed values. Then you take those 64 values and you put them through a 2-layer neural network with a value attribution after the first layer and a sigmoid after the second. And this adds nonlinearity to your model. And at the end, you will adjust your channels based on these weights. So this is kind of what it looks like. This is your first squeeze portion here, and then we do the excitation. And so a CeresNet or SE-ResNet, SE-ResNext, and our variants of ResNet and ResNext, respectively. And what these variants do, they add one SE block of squeeze and excitation at the end of each of your residual blocks, the non-identity branch of your residual block. And this is why we covered everything. Your first place solution did it all. Your ResNet, there's a question over there.
Yeah, sorry, could you just go back a second?
Yeah.
Do you know why this is called squeeze and excitation?
Squeezing makes sense because you are taking a global average of the channel, of the feature maps of your channel, and into one single value. So squeezing kind of makes sense. Excitation, I don't know why it's called that way. But I guess because you're taking values, you're putting them through neural networks, you're exciting your values, you're adding nonlinearity. Maybe that's the understanding or the
Yeah, I think the last time I read this paper, So the intuition behind it is they are like adjusting the feature maps,
Yeah.
and then they are like emphasizing the signal and reducing the noise, like from the rescaling done at the reweighing
so
at that feature map.
I took a look at the paper as well. They were talking about looking for codependencies between channels. So I can understand that portion a little bit.
I just have a quick comment. We might be suffering a little bit as a group from kind of differing skill levels here. So I know there's a lot of new people, and I know convolutional neural networks might just go right over your head. I've never even heard of them. So what I'm going to do is I'm going to post kind of a good YouTube video introducing them. And if you are really interested in some of the stuff that's done here, you can kind of go back and look through these slides again.
I should have put a CNN.
No, I don't think it's anybody's fault. It's just what's going to happen as we kind of move
I'll
forward.
take the blame, and Bruce a little too, but I'll take most of the blame. Anyways, so first place, they tried it all, and basically the whole point was we're going to try every type of CNN under the sun, 1 to 3 channels, image sizes of 112 to 256, and we are going to pick one that works best. So the best model got 0.946, and that's the one that they chose. So that was CNNs. Second part, RNNs. They did an LSTM. They said that they tweaked the architecture. I don't know what that means exactly because they didn't elaborate on this, but they said tweak the architecture, remove, dropped out, and that best model achieved 0.89. And then they did their ensembling with boosting. And they put this down as the way that they did boosting. So for each sample, collect the top 10 probabilities with the labels, and then convert these 10 into binary outcomes. And your binary outcomes is basically just going to be a 1 true, so 1 correct label, 0 otherwise, so it's going to have 9 negative samples, a single positive. And then each model is 1 feature. This I tried to make sense of a little bit, but they said that at most 1 record, or 1 column per model is what you would get. And then they put their secret sauce here. And this is their phrasing. So if anybody Russian in the room understands what that is, or
That's like a little bit of like just a tiny bit of
Tabasco, tiny bit tobacco, a tiny bit of tobacco. So that's our secret sauce. Tiny bit of tobacco. Great. So he came to the conclusion, he was saying that somebody else had come to that conclusion as well at a different time, that in the test set, because remember there's 112,000 records in the test set, that they were equally distributed among the 340 classes, which means that there are 330 records per class. And so what they did was they would fine-tune their output a little bit so that until they would get this 330 split amongst every single one. Question?
Yeah, actually, I thought about it before you actually put that slide on, like if anybody did that. And also, did anybody looked at the combination of the probabilities? So if it's like Eiffel Tower and Hanoi and like tent. So when you have a prediction, like just having not only these, like looking at the probability of the class, but also like a probability of the class in the combination of 3 classes. Did anybody talk about that?
Not that I saw. I think that's a really good idea to essentially group or cluster drawings or classes, but not that I saw on my skim through of the discussion board.
I was going to comment about this. Interestingly, Kaggle, a representative of Kaggle, actually weighed in and said this was actually not the case. So they hypothesized that the test set was perfectly balanced, right? And then they like budgeted their predictions in order to create a balanced predictions. It turns out, apparently, for the record, according to Kaggle, that actually it wasn't perfectly balanced, but it was kind of roughly balanced, and that's kind of what you'd expect in any case. And you'd still get benefits from doing this if it were roughly balanced. Yeah.
Well, they came to this conclusion. So, and they estimate an increase of 0.7% per model. So, and then lastly, we come to blending. Yeah.
Is this similar to Alexi's balancing trick on the Bayer stuff? Is it the same?
No, it's different.
Okay, maybe I didn't understand what this balancing is. I didn't figure it out.
So I've previously presented here, and I've talked about the rebalancing predictions, and so these models produce like probabilities, right? And so if you have this sort of prior knowledge that you expect like your test set to be balanced, you might adjust your probabilities. This is like explicitly kind of budgeting. You're like, I'm going to find like the 340 like most Eiffel Towers, and then I'm going to stop, right? Or something approximating that. And so it's just like much more extreme. It's almost like you could do like an integer program in order to like bin pack optimally here, but it'd take forever to run.
Most Eiffel Towers. I like it.
So this is basically a way of gaming the competition.
Yeah.
There you go.
Probably,
On the bottom, I think.
it probably doesn't produce a very good AI. It just wins you a competition.
Yeah, and that's something that you will see a lot in Kaggle competitions, that people do things that will be very specific to this competition, will help them get to the top spot, but might not generalize the best.
Sorry, guys, I'm maybe a little bit slow here. I don't still fully understand what exactly is happening here. Can you walk through it? Like,
I mean, we have like a little example. Like, so apparently there's like bus and school bus are two of the categories, like very easily confused, right?
I think there was fire and campfire or something like that.
Yeah, but if you like, and so if you predicted like 500 buses and 100 school buses, but you knew that it should be 300 and 300, you could change your predictions.
so you can scale every single prediction across the entire.
I would probably take like the top 300 buses, and then I'd keep them and take the 200 least likely buses and assign them to school bus instead, or just suppress them completely.
The most busiest buses.
Yeah.
Oh, this is
Right.
test time. This
Yeah.
is not during.
Yeah, this is purely test time.
Yeah, there was also cake and birthday cake. I know that.
It's just okay.
Yeah. And then lastly, he did a bit of blending. So how are you going to ensemble these types of models when it's going to give you a bunch of probabilities? And this is how they did it. So I put together this little Excel spreadsheet to show you how this would happen. So here are 3 different models, right? And so first one, Eiffel Tower hat canoe, tent frog hat. For the second canoe, Eiffel Tower frog. And what they did, so per model, you're going to weight them. And he weighted them 2, 1.8, and 1.6 for your best to worst models. And then also for your words, for your place. So first, the first place word is weighted 1, second place 0.5, and second 0.3. So the original blending script that was provided by somebody else had a 5 minus I, so it would be 5, 4, 3. He changed it to resemble more of the MAP at 3 metric, so 1, 0.5, and 0.3. And then you would just kind of multiply them together, and you would get the results that we have there on the end. So after blending, Eiffel Tower, canoe, and tent would come up as 1, 2, and 3.
I'm going to take the opportunity to express an opinion here. I think this is like misguided, by the way, just for the record. Like I think, I mean, they're trying to do something like to optimize for this competition metric, right? And so they've done this sort of 3 thing, and they're trying to do this sort of weighted voting game that they're playing. But like, I assert that like maximizing the competition metric is the same thing as attempting to maximize your accuracy at 1 or at 2 or whatever. Like, and it's same as trying to optimize your negative log loss. And so like what I did is, I mean, I ensembled at a probability level, Like I didn't like find the top 3 probabilities and then find them for everyone and then try to blend it in this way. I think this, in my opinion, this is misguided. Yeah, but they won, so there you go.
He's calling it rubbish, is what he's. All right, and then, question.
So not on this, but I'm curious. Quite a while ago, this is when Quentin presented on the right whale, and they did like passport photos, and they've seen like people draw different sizes. Was there anybody who talked about scaling the images so they'd all be the same size, and maybe even flipping? If you're right-handed, they'd change the left-handed drawings so they're right-handed, so it's also easier to see what's happening.
Not with the second point. So I didn't see anyone talking about that, but with the scaling portion. So I'm gonna have to go back a bit here. So I've kept the axes in here for a reason, and you can kind of see that some of them, so the first 2, they go about 0 to 250. Well, actually the anvil is a little bit in the corner. The baseball is basically 255 to 255, but if you look at the cactus, it's kind of squished, right? It's 0 to 80 is the x-axis there. So it depends on if people are doing it on their computers, if people are doing them on their smartphones, that scaling is going to be different. So people did resize them for the purposes of the convolution. Yeah. Yeah, so you can see if you were to just look at these, you would almost think that they are all the same size. And that's kind of what we want, because they are all a little bit different sizes depending on how you draw them.
So I have a question in the assembling. So what's the assembling part, the blending part? So what was the submission now for that example? So
The submission?
Yeah, as in, what did he really submit as the
So it'd
value
be
for that?
on the right there, it'd be Eiffel Tower, canoe, and tent, would be this, right? So he did like a sum product in Excel, if you were to do it that way.
Okay, maybe I'm actually around the end of it.
I haven't seen anything. Do people? So the input data was basically a bunch of end up being like points and.
Yep, they were ordered points, so
yes.
ordered in the stroke.
Does anyone talk about like basically turning those into like those images that you're talking about and like taking RGB values of that, like basically just looking at the image of it and not just people. Okay.
Yep, a lot of people did that.
I'm just worried by that question, and so I'll emphasize that. So that first group, 2 slides ago or whatever, of solutions, these sort of CNN models. Okay, one more slide, I guess. Here. It's so that the strategy there is to take these strokes and actually draw them, right? So they start as these vectors, but we turn it into like a rasterized grid, like actually we had on the screen, right? Yep. So then you can do a CNN on it. If the next slide though. So these RNNs, then you wouldn't do that. And so you'd treat this sequence of data like as a sequence, and then you'd model it in that way. Yeah. And so there were different approaches there.
I guess the question was maybe, now I have this question. Was it like colored or was it like black and white?
Are you going to cover that?
Color or black and white. So if we look at this, he says 1 or 3 channels. So 3 would be RGB, 1 would be black and white.
But you might ask, where does the color come from?
Oh, where does the color come from?
No, I understand where the color is coming from.
I don't know
but
if you do.
I was thinking like if people try to use colored and black and white.
Yeah, both. Okay. Be able to, like I said, this first place solution, 1 or 3 channels, so he's doing both here. He's doing black and white for 1 channel, RGB for 3 channels.
At the same time. Is that what you're wondering? At the same time?
They're not proper RGB though, are they?
So the data is like not natively colored in any way, right? So if you wanted it to be 1 channel, it's fine. It's kind of one black and white drawing. If you wanted to have other channels, you might have to come up with color from somewhere.
No, but I realized that the
and not
colors
in this
they took
way.
from like a sequence, like what you did first and then.
Right, but so I would say they probably weren't doing that.
Yeah.
That they came up with other strategies for colorizing their images.
You think they did something else?
I'm certain that they did. Yeah. So they would like there was a public kernel early on where they would sort of do time-based coloring. So like the earliest stroke. No, but this is kind of arbitrary. These are like categorical colors. But you might actually interpolate. Like it's slowly redder, like as it gets later, perhaps. Yeah. And so now it's like that color has a sort of a linear meaning with respect to time.
That was my understanding that
Yeah.
that's how it's colored in the first place.
Okay, so those colors that Matplotlib give you, they're just kind of
These are just the
They're not
default colors, but anybody can customize their colors in any way.
So
that they
you
want.
mean like you can go from red to blue basically and go on a scale like
Yeah.
from 0 to 25 to 55.
Just on the topic of the coloring of the lines, do you think that there would have been any value to using a color scheme that was actually, I guess, continuous, like a Viridis or something like that? Sorry, I should go back. So, like, there are color maps that have some very nice properties where you could essentially, like, plot the whole thing and there's no discontinuity, at least in the human eye. So they would kind of blend a lot better than those categorical ones right over there. Did you see anything about people like changing up color maps and saying like, oh, actually this seems to work better than just the default Matplotlib?
No, I actually did see some discussions saying the other side, saying, has anybody seen of any color maps that work? Right. So it does seem like people are playing with color maps quite a bit, trying to figure out if that impacted the accuracy of the model at all. Question? A lot of questions today. I'm trying to speed through this for Alexi, but I don't know if we will.
Sorry if my question seems a bit amateurish, but I'm trying to make up, like, to understand, like, what's going on. But I have a small doubt on the topic with the colors. I mean, following up with him, he said the grading of colors, like a darker gray and then shading it down to white to note like the impression where it began first. Is there anything like that? I mean,
I didn't see any like grading color.
I mean, that
schemes.
can add up to an understanding whether he was right-handed or left-handed based on where it started.
Although to that point, I would say maybe the time-based might actually be a better approach. Because time-based, then it would tell you whether he's left-handed or right-handed, whether the person is. Because the way you start, that's going to be one color, and then as time goes on, you're moving towards the other side. Then it's going to change color. Is that, am I understanding the scheme well? Okay.
And also with the coloring difference, like the first beginning and the end being in different colors, like starting with like what? Is there a methodology which identifies or differentiates like not everyone starts to draw a baseball with a circle, like few draw like the side ones and then few. How do they differentiate, or do they use a methodology to identify like
so
the percentage of people who start with the circle? Or
yeah, so in regards to the order that they draw things, again, kind of goes back to the discussion of is there any color map that makes a difference for these? And I would say the same thing with the time base. If you start in a different part that somebody else would, then it's going to throw things off, perhaps. And so for the color schemes, it's a little bit for our vision. It's a little bit for the CNN as well. But as far as what's better and what works, we are only dealing with full images, right? So complete. Whereas Google AI would be trying to guess while you're drawing it. So perhaps in that regard, a time-based would actually be the best approach, I think. I don't know if I even touched your question to say, yeah, but thing is the whole color map thing is kind of up in the air. Nobody can agree as to whether it makes a difference or not. Got a question up back there? To Mike?
I was just going to say that does a color map add any information that the time series doesn't give you? So you've got the data already included. Why would you then color it because you could just include the time points in your data stream.
So I'm not understanding.
Well, you've got the time points of when each point happened. So if you do a spectrum colouring of your drawing based on time, why would you go to that effort? Because you've already got the actual time points. You've effectively got a spectrum between 0 and 20,000.
Maybe somebody has a comment on that.
Well, because if you want to feed it into a CNN, you can't really feed a time directly into that. It interprets like color channels, right? So if you encode the time as a color, then that means you can feed in something that the CNN will actually recognize.
You had a question back there. Point is, the whole color debate is still very much alive. Press the bottom.
So at the beginning of discussing the solution, you mentioned they train a whole lot of models and then they pick the one that performs best. Is that right? So I'm just wondering how you would actually do that. So I can imagine they maybe have a validation set where they are measuring the performance of these. But if you tune many different algorithms on a validation set and then you pick the one that does the best, aren't we going to end up overfitting? So do they explain more how they do that? I'm thinking about something like nested cross-validation, that kind of stuff.
So as far as the best one, I actually believe that when they said best model got 0.94, it might actually be the leaderboard, the public leaderboard that are choosing. Matt has a comment.
Hey, so nested cross-validation is incredible and everyone should use it only for small data sets. If you were to try to do something where, in this case, where there's like 49 million in the training set, you'd basically never get anything done. So
yeah, I agree that doesn't make sense when you have such a huge training cost to do cross-validation.
Yeah.
But maybe I'm thinking that maybe you should have like 2 different validation sets. On the first one, you tune your models. On the second one, you measure which one does the best.
Yeah, actually, this is an interesting idea that has been shown before. I think early stopping has kind of fallen out of favor recently, but there was a technique where essentially you would train until you think you were done, and you would test against a validation set that is not your actual validation set. It's just another kind of sliver to avoid exactly what you're talking about. Like you were 100% right about overfitting to your validation, and that has happened before. We can't really know what this guy did because he hasn't shown, but like that is a very good idea.
I do believe that it is public leaderboard evaluation metric though, because I believe he talks about validation scores at some other point. It's not related to this. So I did think that he just tries everything.
Yeah, I agree. I absolutely believe that basically, like in Kaggle competitions, people frequently treat the public leaderboard as their validation set. So they make a submission, they see the score, and I absolutely believe that if you do that, you'll overfit to it. And I actually believe that this team did. If you studied the difference between the public leaderboard and the private leaderboard, they actually, so I don't know if you're aware of that detail, but like during the competition, you can submit and you get this score, but actually there's this other set of data set that they finally reveal scores on. And they actually dropped considerably, even though they were down to first, they dropped quite a long way. And so I think they probably did overfit. And so the answer is I think they did nothing about that and just kind of embraced it.
I don't know if this is the norm in competitions. For this one, 9% public, 91% private of the test data. Just for that. Okay. Question? Okay, not you. Okay. The question's back?
Okay, I have a question. Rasterizing the image and feeding it to CNN is quite expensive. Considering how light the drawing is there any technology which can be run on laptop and would still get 0.95 in this competition?
I don't think with the CNN. there were RNN approaches and boosting approaches with the data of just the raw vectors. And so I would say if you have limited resources, that would probably be the best way to go.
Except that RNNs are pretty slow too, for their own reasons.
So there is no best way to go. Get a GPU. That's okay. The question there. I'm sorry, Alexi.
Was there ever any evaluation of how a human would do on this?
Not in the discussions.
I'm just kind of wondering how much sort of training you did on garbage.
Yeah, I'm not sure, but just based on my personal drawings, I believe that I could recognize my drawings.
On that point, I will say, I would estimate that a good 5 to 10% of the training data was total garbage. People sort of didn't draw the thing they were supposed to draw, or they sort of started drawing and then got frustrated and scribbled the whole thing out.
Actually,
you got a lot of that.
That is true. So I was looking at other images that I didn't put in this slide, but there were some where people would start drawing something and just start scribbling because they're getting frustrated that they can't get it and they just give up. So.
And local cross-validation scores on the training, it could get a competition metric of about sort of 90-ish. And if you submit that, you get 94, 95. So the test set was considerably easier than the training data because I think they kind of cleaned it and the training data had a huge chunk of complete garbage.
Yeah. Oh, Matt.
You want to start? You talk first.
Which
I have
Matt?
a question that's a bit of a tangent. What's your question about?
Sorry. So we know on the test set that the human baseline is going to be 1, right? Because it's all defined by what the human said it was. Yeah? Yeah. Disagree with me. Yeah, go ahead. Yeah. Yeah, well, actually, do we know exactly how they were labeled? Was there like a 3-person group? No. Okay. It's just one of these interesting things, even though you're going to disagree with me, is that oftentimes these AIs are not predicting the platonic ideal of what these things are. They're predicting what would a human think.
Yeah, I really like that question. I always wonder in all of these Kaggle competitions, how impressive actually is this? I have a question for you. Dealing with noisy data sets, dealing with a lot of labels that you might not want to essentially backpropagate on because it's just an incorrect label. Is there anything specific you did to kind of handle the noisiness of the data?
So there was discussion where a lot of people seem to have the hypothesis that that's what would win this competition. I disagreed, and I think everyone who did well disagreed. I think basically nobody did anything about it. I mean, you're motivated to have a larger batch size as a result, and so I did things to increase my batch size that I might not have otherwise done. But I mean, you could, for example, take only the recognized images, but I wouldn't recommend doing that because you're never going to outperform Google's AI then, for example. And so, yeah, sorry, do nothing. Yeah.
Okay. Can I?
This is a comment actually. Actually, there are some papers where noise actually helps you train better. So, so there are some kind of noise, not all kind of noise. So probably is the good noise in your gradients that will help you even generalize better. There are papers on that.
Yeah. I could actually go on.
Okay.
Be selfish at this point.
So before all these questions, I had one slide left. So, no, are you sure?
Okay, well, maybe I'll go quick. So people didn't remove the noise, but what if you did the opposite and added more noise to see how well you could get some of those other weird, crazy ones? Randomly flipping in the the junky ones, so hopefully you could match crappy stuff.
Okay.
Yeah.
Okay.
I've always been thinking of. No, actually.
Okay. All right. It's one slide, and all it is that the 5th place solution, in addition to 3 CNNs, he didn't specify what they were, But in addition to those, he also added time information. And I saw a lot of people adding time metrics from the raw data into them. So here he had a delay, draw time per stroke, as well as number of strokes. Yep, and kept increasing his. So this part confused me because this is all he says. It kept increasing his batch size. So I'm guessing he just kept trying different batch sizes until he couldn't anymore. Alexi has a comment.
Quick interpretation of that. So as you're training a network, you tend to lower the learning rate as you go. Although recent research by some people has suggested that you should keep the learning rate the same, but increase your batch size.
Okay.
And I did like kind of both. But so you could conceivably like increase your batch size. Now, normally these things are like limited by the size of your GPU, but there are tricks that you can do to kind of, it gets very slow. And so that would be my expectation. They probably started like 256 or something, and then partway through the training, doubled it, and then doubled it again.
Okay. So I got up to 10,000 and achieved 9.53. So on that note, it is Alexi time.
Okay, so I have like a limited amount of time. So I don't need this.
You don't need that. Is your thing on?
Yeah, you got like
Yeah.
Press and hold.
Alexi,
Yeah.
I'll give you my laptop.
Okay, yeah, sure.
Yes.
Testing 521. No.
Nope.
Oh, it is there. I'm just.
Oh.
Yeah. You just don't hear yourself.
Yeah.
But it's,
Okay. Okay. So I wanted to address sort of the last question I think that you had, because I'm going to talk a bit about kind of color here as well. And so, yeah, so we have time, and if we wanted to pass time to this image network, like how might we do it? And so instead of drawing just like a black and white drawing, we could have like the earliest pixels kind of the lightest color and the last pixels the darkest color, and we've put time in. So that's one thing. Like, why is it RGB? Like, what the hell are people doing? And so, I mean, the primary motivation here is that people are using or want to use pre-trained networks. So people train this RGB network on ImageNet and they want to reuse it, which kind of, I mean, frankly, I think is a little misguided as well, because it's 49 million training records here, right? Like, we can start from scratch here. It might take a while, but there's no reason for us to lock ourselves into this RGB world and do, frankly, like ugly hacks, right? I mean, that fifth place solution there, right? Like, so they like in one of the channels, I guess the red channel, they took like maybe how long between strokes or something. I don't know what delay values were. And then they took how long the stroke was and they put that in G. And then blue was like how many strokes there were in the image or something. Very like weird, right? But that's just they're trying to conform to these RGB images that were trained on ImageNet. And so I took a different approach. Okay, so what attracted me to this competition was that, like, I think the obvious solution is obvious. Like, what everybody basically did is the first thing anyone would think of. It's like, okay, you've got these strokes, just turn them into an image, right, and then do a CNN on it. But it seemed to me that processing the data in its more native format should be more powerful. And so I like the RNN solutions more than I like the CNN solutions because of that. Now, they didn't do as well, although Ross Whiteman, who's not here, had like a very good performing RNN, possibly the best one in the competition. So you can ask him about it if you want to. But I spent weeks on PointNet style approaches. We read PointNet in the reading group, some of us did. It struck me that these drawings were sort of a point cloud or perhaps a cloud of segments. I did a lot of work there. Kaggle is a hell of an environment to try and do research in. I eventually abandoned that and moved on to something else. And so here's my solution. I'm probably the only person who did anything different. Okay, so let's just look at my diagram because I'm going to try and make this fit into time. So this is essentially the standard approach. We start with basically the raw stroke data, and we have this pre-processing step where we rasterize the image and we do some ugly hack to get RGB, right? We start with like a pre-trained image network, probably a ResNet. I mean, most of those models, all of these SE ResNexts or whatever, it's a ResNet architecture in its core. So typically, like, you're going to start with, I mean, like, the standard ResNet resolution is 224 by 224, although people picked different sizes, as you showed. Right at the start of a ResNet, there's this 7 by 7 64-channel convolution, and then this max pool. What that means is you end up with now like a 56 by 56 image with like 64 features, 64 channels, 64 feature maps, whatever words you want to use. Then there's this ResNet core, and we spit out a classification at the end. And so essentially, my insight was, we're going to start with the same data,
but I want to do some processing of it in its raw format as a sequence. And then I figured out that I could actually take these strokes and draw them into an image, but do that in like a differentiable way. Like I could actually have a neural network module that takes the stroke and turns it into an image. And so if I do that, I can, if in the sequence model, I essentially compute 64 features like per segment or stroke or point or something like that, like I could then draw these 64 channels into an image. And so rather than some RGB hack, like the neural network learns these features. And like I think of Bruce when I say this because he's brought this up a number of times over the years. That like one of the things we discovered in deep learning, especially for computer vision, was that we shouldn't be like hand engineering features, right? Like ideally, the model learns the features from as raw a data as possible. And so when people are coming up with these rules to turn strokes into RGB, I mean, that's hand engineering features. And so if instead the model can do it, it should be much more powerful. And so that was my high level approach. I end up kind of in roughly the same place. I could have drawn into 56 by 56, but just what worked for me was something slightly smaller. This is the same as starting with an image that's like, I can't remember, I think maybe 128 by 128, something like that. That's what you would get to if you'd done this. So that's roughly the resolution I'm playing at. And I get sort of a benefit of both worlds here, right? Like I get this sequence model, sort of native format data processing, but later I get this sort of efficiency that we get from convolutional neural networks, right? We just like slide these boxes back and forth, do these really efficient matrix multiplications. We get a good sense of proximity here. Like here I'm just processing like a stroke, and I don't really know that this stroke is near other strokes. They're kind of in isolation. But once they're in an image, now nearby strokes are starting to mingle. And so you get this sort of dual speed approach. Do I have anything over here? Yeah, I mean, like if you just draw the image straight up, you just totally discarded all of that useful native information. Like the fact that this stroke goes, I'm not in the camera. Oh, I am. Hey, like this stroke went all the way from up top all the way to the bottom. Like this is related to this in some interesting way. And when you draw it into a picture, it's just gone. You threw that away completely. And that connectedness information is worth leveraging. And I made that point about convolutions. So then this is like, I mean, sorry, this is like hard to communicate. I haven't had a lot of time. This competition only just ended, but I'm just going to do my best. So here's an example stroke, right? And it's essentially a series of points. And it's essentially defined by X, Y, and T, right? And so here I have N, where I guess N is 6. I made a design decision to change this data. And so I differenced the X's and the Y's and I averaged the T, okay? Which essentially means I used to have 6 points, but now I sort of have 5 segments, right? Where this is the vector that's just down and to the right, and this is down and to the right. But I still kept time. And so the motivation for this, like when you're doing computer vision, you have these opportunities to like deliberately deny information to your model. And so by doing this transition, my model's only capable of understanding the shape of the stroke, and it knows nothing about where in the image that stroke is, right? And so, I mean, when you're finally doing classification, it matters that, like for an umbrella, it matters that this shape is high in the image rather than low. But early on, I might want my model to just be learning shapes, like some kind of translationally invariant definition of shape. And so I deliberately did that here, but I wanted it to continue to know time, because we all know time is important. Like if I just got DTs along here, they'll all just be small numbers, and we'd get some sense of how fast the stroke was drawn, but not like when it was drawn. And I think as Izzy sort of motivated for us, like the early strokes are way more important than the later strokes, especially when they start to scribble out their drawing. And so I compute these features. I do a 1D CNN. So essentially, I'm sliding a little window back and forth here. And we could get into the details, but we won't. And so then I essentially create a set of 32 features for each of these, right? Now they're just abstract. Who knows what they mean? They started at this, but the network has learned to make 32 features. Now, my rasterization module really needs points and not segments. We'll get to that in a moment. So I have like n-1, I have 32 features kind of for each of these segments, but I really wanted 32 features for each of these points. But I can get that essentially by like sliding a window across this, right? And so the first window kind of hangs off the end, and then it slides to here. And so then there's actually n of those windows. And so I can do this, and it's like a presenter trying to communicate like convolutional math is a bit hard. But if you had a kernel of size 2 with a stride of 1 and a padding of 1 and then 0, I can take this n minus 1 and turn it into n. And if there's 64 feature maps, I now have 64 by n. So essentially now, like for each of these points, I have some kind of feature vector that captures kind of the 2 segments on either side of it. Except that my 1D convolutions had a receptive field, right? So actually, the feature here kind of includes some information about how this banded, depending on how like wide that receptive field is. And so now that I have 64 features, 1 for each of my original points, and I also have an x and a y for those original points. And so now I can do my rasterization step. So this is my kind of, oh, look, it wrapped. That's funny. Anyways, so 64 by n matrix. But I know that I know the x and the y coordinate of that first point. So in my little drawing that I'm creating, got like stretched or something. Let's see if this is gonna work now. Yeah, so like I have this teal x value, and I can look up in the grid where I think that should be. And so here along the x, this is like a 32 by 32 image. Like this is its x coordinate. And then this is its like y coordinate from the dark blue. And so I can take this 64 vector and I can like draw it into the image right here. And then for each of these, I could look up the index of this point and the index of this point, and I could say that this feature vector belongs here. And so my stroke can now be sort of drawn into the image, but rather than just this black and white on-off, was it here, was it not, I have 64 features, and I can draw 64 images that capture a kind of a richness of it. Like 1 person caught up, yes. Matt gets it, maybe. No, he gets it enough to ask a question. Sorry, it's hard, and I didn't practice that.
Do you have any idea what is being encoded into this?
I tried visualizing it. Like basically, you get 64 little black and white images that you could look at. It wasn't. I didn't get it very far in interpretability. No.
I'm sort of assuming that the raw data is in like a variable length sort of format. So they have a different number of points for different drawings. Is that correct?
Absolutely. It varies extremely.
So how do you handle getting it down to a fixed length to input into this?
Yeah. So yeah, I needed a fixed number of points. I probably could have engineered my way around it, but like time is limited. I essentially resampled it to 256 points. So I took like all of the strokes and all of their physical lengths, and then I kind of budgeted a number of points for each of the strokes based on an amount that would get me to 256.
Okay.
I ended up with like smoother strokes as a result, because it's you kind of like when you're interpolating something that's sharp, you end up with smoother. But yeah, that's what I had to do.
So I guess I'm also wondering, this sample that you're doing of the 256 points, since you already know what the vectors are you, since you defined in that previous sequence module, did you do any sort of like, I guess, data augmentation by just actually randomly sampling different points along these vectors?
Okay, so an interesting property about this competition was infinite training data. Like seriously infinite training data. Like my models that trained for like 3 days and were like possibly the best single model in the competition, I don't know. Like they saw every data example maybe 1.5 times, maybe. Like I don't think I ever completed 2 epochs. Right. And so no reason to data augment whatsoever. True. Like True. You never run out of real examples.
So at the start you said you had a sequence model to feed in. I'm less familiar with like RNNs as I am with like computer vision, like CNN. So is it what kind of like layer to get those 64 features? Kind of what kind of layer or model do you get? Like I probably just missed it, but
no, yeah, I mean, so first of all, like I didn't do an RNN. I would have liked to, but I'm just not familiar enough with them. And so, like, you'll be familiar in a CNN where we have like this maybe 3x3 window that we slide in a 2-dimensional way. So a one-dimensional equivalent of that is like a one-dimensional window of, say, 3 that we slide back and forth. And so first we process these, and then these, and then these. And if we padded it, we could have done this window, this window, this window, this window, this window. And then you kind of stack those convolutions kind of in exactly the same way that you would in an image. Yeah.
I'm interested, how did you train those two parts of your model? So like the sequence model generating features and the ResNet, I guess. Was it at the same time or?
Yeah, so I could do this end to end. Yeah. And so like this process is not differentiable for X and Y, right? Like I couldn't tell you if you moved X by a little bit what the impact would be, because it's kind of this, it has these serious discontinuities at these points, right? But I can pass a derivative from here up into there.
For me, it kind of reminds the model of GANs. So it seems like you have a critic in the end, basically, and like these things that generates features. Do you consider it to be kind of like the same approach? Like you have two models, and one of them trying to learn how to generate features, and the other one how to predict those features. Is it?
Yeah, I'm not familiar enough with GANs to really, yeah.
I think the better model to think about this would be like a variational autoencoder, where you're having this one part that is trying to transfer some sort of information to the second part, and they're working together, whereas a GAN is trying to, essentially one is trying to work against the other.
Yeah, encoder, decoder. Okay.
Yeah. The sequence model is trying to encode it in such a way that the image model can make use of it better. Yeah. And then maybe just some other comments. So yeah, there's a lot of non-trivial engineering here that I didn't get into. I had to write my own PyTorch module with the forwards and backwards to make this happen. I was using the latest PyTorch at the time. I used NVIDIA's Apex automated mixed precision, which, I mean, definitely Bruce has made me question my speed ups that I may have got from that, but I absolutely got way bigger batches. Like basically I got to double my batch size, and like nothing is exhaustively explored because this is a Kaggle competition, not research, but like it was generally considered amongst the community that a higher batch size would help deal with the noise. And so I sought that. And so I was able to double it in this way. I also used this is a PyTorch method. There was something you can do in Keras too, apparently, to accumulate gradients. So essentially you run 2 batches before taking a step, and you kind of add their gradients together. And so you sort of increase your batch size when you do that. Batch norm set aside, you do increase your batch size. And so I was doing that. So as I trained, when I thought that I was on a plateau, I would maybe like halve the learning rate and double the batch size. That was my kind of formula that worked well. Sorry, it's just alchemy, but that's what I did. And then I'd do that again. And then maybe at the very end, I'd crank the batch size up to like 8, and like just to beg for those last little points, because as you saw, the competition was really tight. So what else did I have here? Like absolutely, I trained on all the data. I used the raw data. I think the simplified data would be pretty good. Huge data set. I did this LMDB memory map database thing that I could talk about another time. I used Atom because it's great. I had access to a system with a 1080 Ti and a Titan. I owe somebody a lot of beer. You may know who that is. And it took about 2.5, 3 days for a model to kind of converge. And they absolutely do converge. There's no overfit because there's infinite training data. I used the pre-trained ImageNet weights. Like, I know that I was like saying that why would we, but like there's almost no reason not to, basically. Here, one more. Like this is all the same, right? So I could chop off this part and do PyTorch network surgery, which you seem to do a lot of when you're a PyTorch person, and then jam pre-trained weights into there. Small benefits, to be honest, but why not do it? I like froze the weights in the pre-trained bit a little bit before, just so we didn't destroy them with early gradients. Again, you can't test these things exhaustively. I can't guarantee you empirically that all of these things work. They're just things I did. I I had 50K that I used for validation as I went, but I held out 1 million for blending later when I was ensembling my models. Infinite data, so why not hold out 1 million? I mean, it turns out that 1 million is actually quite a lot. Like, if you have like 12 models, each that have made 340 predictions and 1 million, like that matrix gets like annoyingly large. That's the part that's supposed to be easy, but I set myself up there. Yeah, I probably never completed even 2 training. I already mentioned that. I don't think I talked any more detail about my blending. I don't know. Nah, we ran out of time, so I can cover anything at any other time with anyone one-on-one.
We can do questions. We can do like a few questions for both the.
Yeah.
So, I think, what about non-neural network techniques that handles like those spatial relationships and the strokes? Did anyone try out something that's non-neural network based? So, or that conventional machine learning?
Not to Alexi's extent. So neural network, there was a lot of CNNs, a lot of RNNs. There was a lot of boosting. So those were kind of the top 3, CNNs, RNNs, and boosting were the 3 main approaches. But CNNs by far the biggest one.
So I used PyLMDB, and so basically you create like one giant file on the disk. I'm not a computer scientist, I just pretend to be one, but like I guess if you know exactly where on the disk all the bytes are that you want, rather than doing this file thing, like 50 million files is a lot, and looking through directories and trying to pull them up and whatever. I actually took the raw data and converted them into unsigned ints so they'd be smaller. Like that's on 0255, so it's just to pack them. So my database was only a few gigabytes. But like, yeah, disk I/O was never a concern for me, where it was when I was trying to load up 512 little files per batch every however really fast. I didn't lose a lot of precision that way. So there was a weird mix in the data. Like some of the, so all of the simplified data was like 0 to 255. But the raw data was like a mix. Like some of it was 255, some of those numbers were like 18,000 or whatever. Yeah. Some of them were ints, some of them were floats. I don't know what's going on there. If I had all the time in the world, I'd be looking for leaks in there. You know what I mean?
Okay, let's give them a round of applause.